Our world is driven by forces and the laws that govern them. Newton's first law states that an object maintains constant velocity unless acted upon by a net external force, a property known as inertia. The frame of reference that we view a situation from can dramatically impact the forces that appear to be at work to keep the law of inertia in place. The first frame of reference is the inertial frame of reference. A frame of reference is inertial if it remains at rest or moves at a constant linear velocity. Now, let's analyze forces in this frame of reference. This is a playground spinner, a fun piece of playground equipment. Viewing the spinner from the frame of reference of the Earth, that is, the person filming is standing on the ground, would be an inertial frame of reference, as it is effectively not accelerating. To replicate the forces acting on a rider of the spinner, a washer was attached with a string to the pole. When the spinner was spun at approximately constant angular velocity, the washer is seen to swing out, away from the center of rotation. This makes sense with the laws of inertia, as there is an acceleration of the spinner inwards towards the center of rotation, and the washer is resisting this acceleration, but is nonetheless being pulled towards the center. This inward force is called the centripetal force, also called the center-seeking force, and is the x-component of the tension force in the washer's string, as can be seen in the diagram. Now, what if we were filming on the spinner? This would be a non-inertial frame of reference. This is a frame of reference that is accelerating with respect to an inertial frame. The spinner is a non-inertial frame of reference because it has an angular velocity. This means that while the tangential speed remains constant, the direction is changing. This means that the velocity is changing, and thus the frame of reference is accelerating. To view the washer in this non-inertial frame, the tripod was attached to the side of the spinner apparatus and tightened to prevent shaking. In this frame of reference, it is not apparent that the spinner is accelerating. It just looks like the rest of the world is spinning around it. Thus, when the washer swings out, away from the center, it appears that there needs to be a force on the washer pointing away from the spinner to counter the centripetal force and to keep the net force zero. This will keep the washer from accelerating back towards the pole. The same phenomena can be seen when viewing the washer from a lower angle. This force is called a centrifugal force, and is something known as a fictitious force. A fictitious force arises when in a non-inertial frame, because we may see objects apparently accelerate, despite being no identifiable force to account for this. Our belief in inertia is so strong, we create a fiction that there is a force causing this acceleration. In this case, the washer has an acceleration of zero, despite the centripetal force acting inwards, which would seem to cause the washer to accelerate in that direction. The centrifugal force is a fiction we introduce, so the net force on the washer is zero, therefore giving it an acceleration of zero. Because we don't know that the system is accelerating, the centrifugal force is necessary to explain why the washer remains at an outwards angle to keep in line with inertia. The force is represented in diagrams with F subscript fict. Drawing another vector diagram, we can again include the centripetal force as the x component of the tension force. The centrifugal fictitious force, however, is 180 degrees rotated with the same magnitude. The gravity and y component of the tension force are also opposite vectors, and thus the net force and acceleration of the system is zero. Now, we will calculate the centrifugal force. First, preliminary measurements were done. The washer mass and the string length were found, and the length of the string in the x direction was calculated based on the field of view of the camera. The angle that the washer swings out at from the spinner, theta, was calculated using the reverse sine ratio of d over dx and was found to be 56.7 degrees. Next, the centripetal force was calculated. Using the free body diagram, the equation tan theta equals the centripetal force over the y component of the tension force was generated. The equation was then rearranged, and the y tension force was substituted for the gravity force, which has equal magnitude. When the correct values were input, a force of 0.556 newtons was the product. This force is equal in magnitude and opposite in direction to the fictitious centrifugal force. Therefore, the centrifugal force has a magnitude of 0.556 newtons away from the spinner's center of rotation. Remember, the fictitious centrifugal force only exists when in the frame of reference of the spinner. As our belief in inertia is so strong, we create the fiction it exists to explain the washer's lack of acceleration. On the spinner, off the spinner. On, off, the end.